Swayam Prabha. Digital India. Educated India.
Welcome. So we have done all this volume averaging for the last few lectures, and this lecture we will try to finish this chapter by doing area averaged models. These are particularly important for channel flows. So there is a basic difference between area averaged and the volume averaged models that we did. Now, area averaging is usually done over the entire cross section, right. So, the entire cross section, okay, and it is distinct from the volume averaging, which is done over a small elemental volume. Volume averaging is done over small, that is delta V volumes. Okay. So, area averaging by default is kind of like a 1D in nature, right, because it is done over the entire cross section. So, basically you have a unidirectional nature of the whole thing, and distribution of properties, that means variation of properties along the cross sectional area is also lost. So, property variation across cross section is lost. Okay. So, keeping these things in mind, let us look at how the area averaging model actually works. So, assume that there are different phases flowing in a channel, So, it is like a channel flow. Okay. So, AC is basically given by the summation, where K are the number of phases. Okay. So, this is the total cross sectional area of that particular channel, which is nothing but the sum total of all the individual areas that are occupied by the individual phases. Similarly, epsilon K, which is basically the volume fraction of the kth phase, is given by this. So, this is nothing but the volume fraction of kth phase, okay. And it comes with the natural consequence that if you sum total all this epsilon k, it will become 1. Okay. So, if you do an Eulerian area average, okay, if you recall all the notations, this is basically given by this, and we will have a small tutorial where we will cover show some example problems that how this area averaging and volume averaging works, and that we will do later. So, it is basically nothing but this. Okay. So, this is the Eulerian area average of any particular quantity that you may be interested in, right. Okay. So, if you recall what was intrinsic averaging, so intrinsic phase average, average is given by, if you recall the notations from the earlier classes, okay. So, that is the intrinsic phase averaging, right. So, when you have taken only the phase into consideration, that means the area occupied by that particular phase. Okay. So, it is averaged over that particular phase. So, extrinsic on the other hand, if you look at extrinsic phase averaging, that is given by nothing but the summation of the individual phase averaging of the quantity that we recognized earlier. So, this is the extrinsic phase averaging. Okay. Okay. So, area averaged homogeneous model basically treats the flow as a homogeneous mixture with all the phases moving with the same area averaged velocity, right. So, area averaged homogeneous models and we will use all these models in different contexts, okay, treats the fluid as a homogeneous mixture with all phases moving with the same area averaged velocity, which makes sense, right, average velocity. Okay. It makes perfect sense over here. So, based on this, if we write the continuity, and we will move fast with this because you have already done a lot of continuity equations in the two volume averaged sections that we did. So, this is basically the, remember one dimension only remains, the other two dimensions are basically lost, right, because you have averaged them out. Okay. So, these are basically nothing but area averaged quantities, area averaged rho and axial velocity. Got it? Okay. So, and as usual earlier, the product of quantities like the deviations of rho and w, we have neglected them, right. So, earlier we knew already that we usually neglect quantities like this, right. Okay. These are basically neglected, correct. This you already knew earlier, okay, from the earlier exercises that we did. Okay. So, this rho is basically nothing but, if there are two phases, more phases is not a problem either. Okay. So, this is basically the volumetric fraction of the vapor in a two phase mixture. That is just a special case. This is the general equation, okay. This is just a special case. If it is a two phase mixture, this is how you should actually write it. Got it? Okay. So, similarly we can write the momentum, okay. Momentum should not be a problem either. Okay. So, in the case of momentum, this becomes much easier because we are dealing with only one dimension, the other dimensions are not there because of this. Okay. So, in the case of this, if you know your pipe flow and other kind of equations like this should become very apparent that why it should look like this. Okay. But of course, the pipe flow does not retain the convective term, okay. But in the entrance length where the flow is developing, these terms will be there. Okay. This is P minus, if there is any gravity dependent gradient, that should be there. Okay. That is the inclination effect essentially, and then P by AC into tau W, okay, where AC is basically the cross sectional area. So, So, that is the net equation, and all the terms are known: inertia, okay, the pressure term, the gravity or the inclination term, the shear stress term, right, the wall shear stress term. So, that is pretty logical. Okay. So, based on this, we know already what the energy, what the momentum equation looks like. So, the energy equation, I am writing the energy equation including the mechanical energy term. Okay. So, here plus okay. So, this is g cos theta. Okay. Just one second. G cos theta. Okay. So, that is the net energy equation including the mechanical energy term. If we just deal with only energy, that means you take out the kinetic energy and all those terms out of the expression. So, this is written on enthalpy basis. So, this term is basically becomes your viscous dissipation, and this term becomes your heat transfer from the wall. Okay. And this is basically the compressible term. Okay. Fairly common. So, this is the net equation. As you can see, it is much simpler than what the volume averaged equations that we wrote. Okay. And so, there is only one more equation that is left after this, which is basically the species balance. Okay. The species equation is almost exactly like the continuity equation, well, almost like the heat the energy equation, sorry. Okay. This is Ji plus the corresponding Mi. Okay. So, this is basically the source and sink term. Now, what is the source and the sink term? Because some species may be actually transferred. That means, if you have a transfer from the liquid to the vapor phase, for example, that is a species transport. If a chemical reaction is going on, that is a species source and sink. This is basically nothing but the diffusion term, right. Okay. So, this basically shows this entire band of equation that we have this, and if we go to the previous one, this one energy, and if we go to the one before that, this is the continuity and this is the corresponding momentum. So, all these things are written now for the area averaged one. Okay. And once we do a tutorial or a sample problem in which we will solve that sample problem, okay, by using a combination of this area averaged as well as this volume averaged, but that will be done later, okay, and that will be supplied as a study material. So, where you can actually take a look, which basically uses these equations and sees how that can be applied to a real life problem. Okay. So, I can give you the problem definition, that how is it actually solved. So, if you look at, for example, this expression here, okay, is from okay. So, if you look at the so this particular problem, okay, and which we are going to solve, okay, this is basically nothing but a cooling tower, so to say. Okay. So, what happens is that air enters here and it goes up. Okay. So, this is basically nothing but hot air, okay, and water is sprayed from the top like a curtain. It is like a shower curtain, okay, almost like a shower curtain. Water is sprayed in the form of this dispersed phase. These are basically dispersed like droplets, basically, got it. So, they are sprayed like droplets, okay, and what do? They interact with this airflow, okay. So, naturally there is a transfer of heat that takes place. So, there is a phase change of water droplets to water vapor, okay, and the air then escapes out, okay, and the water afterwards collects at the bottom. Okay, but we are not concerned about this, or this you can say it is instantaneously drained out. Okay. So, if we have to analyze a problem like this, we can use both the multi-fluid formulation using the volume average. So, this can be done by multi-fluid formulation, and we will give you as a write up multi-fluid formulation using volume averaging, right, that can be done, and we will try to see whether it can be done through area averaging also, because it is like a constant area section, things are occupied by the two phases. Okay. I mean, this problem does not have a numerical answer, but it is basically how we can cast our equations. Okay. Because as you can understand, most of the multi-phase fluid problem do not have a numerical answer, because it is a complicated physics, right. So, we are going to only be able to cast it in certain forms, right, that how we are able to cast it. Okay. So, we can write some of the assumptions, and this is just to kickstart the problem, not necessarily do it. We can assume that the flow is steady, because that will get rid of the transient terms. Okay. Okay, it is planar. It is a planar flow. Okay. So, that means there is no z variation. Okay. So, z variation can be neglected. There are no pressure effects. I mean, these are all assumptions. You can solve the problem even including that. Okay. Just will make life a little bit simpler, and product of the deviations, as we already did in our derivations, deviations is 0. Okay. So, using these assumptions, can we write down what is the continuity, momentum, the corresponding x momentum, y momentum, right, okay, and the corresponding the forces that are acting on the system, right. Can we actually write a complete, can we cast this problem basically in a nice theoretical framework with all the governing, and with all the governing equations, write down all the boundary conditions. Recall these walls are insulated, so you can have actually a zero heat flux condition at these walls. So, all these things we need to cast, okay, and show that this can be solved by the multi-fluid formulation using volume averaging technique that we talked about. Okay. So, this will be given to you as a write up. Okay. So, you can study that write up. You can also read it from the textbook for this course, which is transport phenomena in multiphase systems. Okay. It is an example problem there. So, but we will also give you a write up in which we will explain the details, right, that how this is actually done. So, based on this, what we have, we can also solve this problem, as I said. Let us see. Okay. As a student, you guys can also try, see if this can be solved by this area averaging. So, that is the question. Okay. Of course, we will give you some answers to that, but at this point this is a question. If you are following the course in a sequential manner, can you also think about casting it in some other way? Okay. So, we will do a couple of example problems like this, okay, and we will give it to you in the form of write ups. Okay. So, let us move on to our journal. Okay, and let us move to the next page. Now that we have covered, we know more or less what these phenomena are. We know what are the governing equations, we know the thermodynamics of the system. So, we have covered quite a bit of materials in terms of getting you a feel that how multiphase systems actually work. Now, let us look at some of the important things. Then this is interfacial heat and mass transfer. And from here we will go on to some specialized topics after this, okay, which will involve mainly droplets. Okay. So, in interfacial heat and mass transfer, okay, the primary thing that you guys already know to a certain extent, there is something called capillary pressure. These are utility things that we need to know, okay, because this will help you to understand whatever we are going to do after this. So, this is capillary pressure is basically Young Laplace equation, and how do you actually derive it, how do you, what is the physical explanation of the same. So, that is what we are going to do over here. Now, if you assume that there is an interface, now look at it very carefully. Okay. This is an interface, so say this is liquid, this is the vapor. Okay. Let us use. So, if there is a fluid, there is a liquid molecule, let us look at the state of the two liquid molecules, right. One liquid molecule, so this is the interface that separates the two, this is liquid, this is vapor, right. Okay. So, assume that there is a liquid molecule which is sitting inside the liquid pool, far inside. Okay. What happens is that if you look at the intermolecular forces that are acting on this, is very isotropic in nature. Okay. So, that molecule is basically balanced from all sides. Okay. So, the intermolecular forces from all sides, okay, are balanced. Okay. So, that is what happens when the molecule is actually inside. Okay. So, when the liquid molecule is inside the liquid pool, far inside the liquid pool, away from the interface, okay, it is basically in a balanced condition, right. So, all the intermolecular forces balance. So, all intermolecular forces, molecular forces from all sides, okay, are balanced. Got it? Okay. And you should also note one very important observation. The intermolecular forces in the vapor phase is weak compared to the liquid phase. Okay. That means the binding forces, intermolecular forces in vapor phase are weak compared to liquid. Okay. So, that is a good. So, what happens to a molecule now which is at close to the surface like this, right. So, what will happen is that this molecule on the two sides, that is Fs, on the two tangential sides, okay, most likely it is in a balanced condition because it is within the liquid, right. Whereas, this force, if we look at this as O and this as Fi, okay, this Fi, which is the pull that is exerted by the liquid phase on the molecule, is sufficiently large compared to the pull that is exerted by the vapor. Because of this reason, intermolecular forces in the vapor phases are weak. Okay. So, what happens is that this is basically nothing but the force in the normal direction, right. Tangential direction is still balanced. Okay. Okay. So, what happens is that this pull, this Fi, this excess force rather, tries to pull the molecule at the liquid vapor interface towards the liquid phase. So, if the molecule is here, the liquid tries to pull it inside, okay, because of the dominance of this particular force over there. Okay. So, in other words, Fi minus F naught, this differential, right, causes movement of liquid molecules okay, until maximum number of molecules lies in the liquid interior. Got it? You can understand the phenomena, right? Let me explain it one more time. There is a disbalance of the force, right? The vapor that is in the vapor phase, the pull that is coming from the vapor phase is weak, and the pull that is coming from the liquid phase is strong. So, naturally the molecule is pulled back into the liquid interior till there is a certain amount of packing, right. So, that the maximum number of molecules lie in the liquid interior, okay. And one ready result of this is that this leads to the interface having minimum area. You got it? So, this leads to the minimum area of the interface. Okay, one of the reason why you can see whenever you have always droplets, right, you have always you do not have a sheet of water, okay, that is formed, correct, unless it is lying on the substrate, that is a different issue, okay. But normally it will lead to this spheres, right. So, because it leads to a interface having the minimum area, right. So, you understood this phenomena that so that is what governs.